So, this example that you saw on VREP and the parallel we drew with the airplane example means that there is an algorithm, right, that is what we said. Way back in the 1980s there was a book written by one person by name Breitenberg, Breitenberg. Okay. This researcher wrote a beautiful book, and the book that he wrote is titled Vehicles Experiments in Synthetic Psychology. Experiments in synthetic psychology. Okay. So, this collision avoidance that you see is often, he devised many algorithms and many experiments, and one of the experiment is indeed the collision avoidance algorithm. He denotes any sensor like a fork, you know, the tuning fork, right. So, his sensor is nothing but a tuning fork. Oh sorry, I must show it properly. So, let me show it like a tuning fork. This is a sensor for him, and any motor is essentially a like a rectangular box, right, a rectangular box. He thinks that sensor should be coupled directly in one of the, in this example particularly, do not so to not to generalize anything, in this particular example if you look carefully, the sensor is indeed the ultrasonic sensor. Okay. These are the ultrasonic sensors, this is the sensor and this is the motor, this is the motor. The sensor and the motor are directly coupled, this is a directly coupled system, and essentially we are trying to see how to use these sensors to control this motor. Sensor is giving some input, motor is doing something else. How is this happening? Now the example that we took where the motor had a set of sensors is shown in this picture. So, let me take another color to explain to you. How many sensors are there? There are 8 sensors, you can see 1, 2, 3, 4, 5, 6, 7, 8 sensors in the front. What sensors? Ultrasonic sensors in the front, and then there are 8, 3, 4, 5, 6, 7, 8 rear ultrasonic sensors. So, what we have done is, in this example we have disabled all of them, we have removed them. Okay. We have kept them there, but we have disabled them. So, we do not use them at all. Okay. So, let me just put back all of them 3, 3, 6, 7 and 8. So, we do not use them anymore, and we take the front 4 which I will show you here. There are 2 motors, right. Our robotic platform in VREP has 2 wheels, each wheel is one motor. So, we associate the first 4 ultrasonic sensors to one wheel which is nothing but one motor, and the remaining 4 to the other motor, okay, or which is nothing but the other wheel or other motor. So, you have 1, 2, 3, 4 and you have 1, 2, 3, 4, all 4 together making it 8. This model you can imagine is very similar to what we have written here, sensor and motor coupling. Now concentrate on this picture. What is the simplest algorithm that you can think of? You have one vehicle coming in this direction, another vehicle coming in this direction, right. Now if communication is enabled between the 2 vehicles and sensing is enabled using ultrasonic sensors, if you am able to communicate the current position of the systems in real time, if I am able to communicate in real time the communication between the two systems, because I have a communication module which is part of the system that we have created, then in real time they know, each one of these robots actually know their current location and at what speed they are approaching a particular intersection. Now once they realize that they are in very critical distance, and how do they know they are in very critical distance? They know that because of this guy. The ultrasonic sensor tells them that they are extremely close. There is a threshold, a simple threshold based system is applied, and if they are within critical threshold distance, the two robots decide to go in two different directions, and that is easy to envisage here in this picture. If you are close, these 4 sensors will get actuated. They will say that they are in close proximity to the other robo, and once that happens you increase the speed of this. If you increase the speed of this motor, this is bound to turn in this direction, right, and therefore avoid a collision. The same thing will happen to this robo as well. Moment it comes within close proximity to some threshold distance that has been applied, the motor, the 4 sensors on the right sense that the 4 ultrasonic sensors sense the proximity, and that motor is increased in speed. Moment that happens, this robo goes away, right, it goes in this direction, and this robo goes in this direction, and this is exactly what you have seen in terms of a demonstration. Who proposed this direct coupling between sensor, motor and all of that? It is all done by the very simple example, and this is nothing but the simplest Breitenberg algorithm that has been coded within the VREP to show you this demonstration. Okay. Now it is so simple but very intuitive. You can use this as a starting point to build very complex algorithms to do collision avoidance. Now different type of metrics can be adopted for distance calculation. One is you can do simple square root of x squared plus y squared plus z squared. If you know the positions, you know the distance estimation of the two robot systems, or you can use other type of distance estimations. So in essence, Breitenberg algorithm is essentially trying to has been coded in this, and it gives you an intuitive example of how you can do collision avoidance. Remember what we said very critically about the point here, that you have to do object detection and then you have to do obstacle detection. So unless you detect an object, you can't do an obstacle detection. All of this means you need sensors, and again you are, in this case we are using ultrasonic sensors to essentially detect that there is an obstacle in close proximity, and then we are moving away from each other using a very simple Breitenberg algorithm, right. So let us capture all of this in terms of some nice high level view which will help you to connect even better on this example. Let us now turn our attention to the program scripts here. This is essentially what is being coded. There is a main script. You know that there are two robots, robot 1 and robot 2. We have taken a model called Pioneer underscore P3DX, to which is associated a transceiver module placed on top of it. which becomes a child. So, the parent will have a script and the child will have another script. So, essentially there are two pieces of code which are working together. The Breitenberg algorithm that you see is quite straightforward. I hope you can read the slides quite well. Take robot 2, let us start with robot 2. Initialize and handle ultrasonic sensors 16, disable 8 of them, not shown here, but you have to initialize all of them because you have taken that model. Initialize and handle 2 motors, our robo has only 2 motors. Send current left and right motor speed to whom? To its child, so that it can convey that information to the other robo. So, read data from parent script, that means it is extracting this information, the transceiver module, and it is constantly sending the data over the air. Whether there is another robot or not is not of importance, it continuously keeps transmitting as a beacon, goes on sending out the current left and right motor speed being conveyed out on the air. Now, if there is indeed a other robo in its communication range, it receives the data over the air and then it does some processing and sends it to the back to the parent, and the parent now says I will now read the near robot left and right motor speed because it is coming from the other remote side, and then avoid obstacles using the Breitenberg algorithm, which is essentially using the ultrasonic sensor and a certain threshold applied to the range. And all of this is going through a communication system. As you can see, it is the communication medium is wireless, and the same replication actually happens on the other robo as well. Initialize and then handle the 2 motors, send the current location, current left and right motor speed, and then read the near robot left and right motor speed from the remote side, other robots left and right motor speed, then also run the same algorithm like 2 airplanes at cruising speed, right. They are just avoid, they have a collision avoidance algorithm. So, quite like that. Alright, so that is interesting part, and now it would be useful to just run it once to connect everything together. There you are, they are coming closer, and you have seen a completely different demonstration now, right. This is your lab exercise. How did this happen? In this experiment, see, an interesting thing happens. Can we run it again? So, there you are, the other robo actually has stopped and then allowed the other robot to go away, which is very, very interesting. Why do not you try this? This you should try as a lab exercise for yourself to learn a little more. This is another type of obstacle avoidance, right. It is also trying to do obstacle avoidance, but of a different type. It is not parting ways, or it is not moving away in 2 different directions, but instead it is stopping and allowing the other robo to pass, after which it decides to pass. The left side robo, as you can see, waits for the right side robo to pass, and let us try that algorithm again. Look carefully, there you are. So, it is now quite simple for you to make modifications to this code. What is actually happening? Now, you can easily modify the following. So, what you should do is, it is quite simple, quite intuitive. The robo here has an ultrasonic sensor, the robo here has a set of sensors. In the first case, what we did was we ran the Breitenberg algorithm to do obstacle avoidance. In this case, if they are in critical distance, you just stop, do not run the Breitenberg algorithm, that is all. You disable the Breitenberg algorithm and but if you disable the Breitenberg algorithm, there is a likelihood that they will collide. So how will you avoid the collision? You have to do some more glue logic, you have to do something interesting. You have to by and large use the ultrasonic sensor to say that if I move a little more forward than what the ultrasonic sensor says, I am going to collide, and therefore I decide to halt. Now both may decide to halt, right. In this case you can see in this demo we have coded in a manner that only one halts. Now you have to take a call whether it should be the left side one that should halt or the right one that should halt. That is a matter of how you code everything. In this case I can give you a hint that whoever is slow should halt, that is all you need to put the glue logic. It appears if you run the demo again, you might not see it directly, but you will see that indeed the left side robo was moving a little slow compared to the one that is moving away, moving straight away, which gave it the priority to do an intersection crossing because it was moving at a higher speed. So what you do now, you take this algorithm basic code which is going to be available to you, apply this glue logic which essentially says I will use ultrasonic sensors to do thresholding, I will put a threshold on it, and moment that threshold happens and I know that I am slow, I have to halt so that I can let the other robo pass. This is all that would be required for you to try and experiment it. Of course I am not going to leave you high and dry, let us try and understand this code, we will run through this code for you, but what will be available on the internet for you to try would be the basic code, okay. Although we will show you here, it is important that you try it yourself in a effective manner. So first step would be initializing the variables. So as you can see, that is initialize the 16 ultrasonic sensors. There are 8 in the front and there are 8 in the back and making it 16 and all that. You are using only 8 that we mentioned this already, but you have to still initialize all of them. Get the handle for the left motor and the right motor, that is also shown there, and then you initialize the sensor range. So this is an important step, right. So you have to initialize the sensor range. Then you create an array of distance measures of proximity sensors. You can see that detection is all zeros, that means you are initializing it all of them to 0, and what is important is to ensure that you are using only the 4. For the left you are using the 4, you can see they are all 1 1 1 1, these are binary, right. 1 means it is initialized, 0 means they are not used, so it is just a binary decision. The left one uses 4 and the right one Breitenberg R uses the other 4, the rest of it are all zeros. So which is a clear indication that they are not being used, alright. Then this is so that is about what we are doing. Then let us go to the next step is to get the handle of the other. Of course there are 2 robots, so both the robots have to essentially work in tandem. So now let us further look at the code. Here you can see that the way the VREP codes it is, you have to understand, get used to the way it codes. Essentially what is sent over the air is the motor speed, right, that is all you are sending, and from the motor speed you are now computing the position XYZ of this robo or my position relative to the other, okay, relative to the other robo. So this is a continuous process, each time you are computing based on the motor speed what is my position, current position with respect to or with relation to the other robot's position. So this both robots are doing this computation, and obviously this distance is coming down as they are coming closer and closer, and then they also note their speeds because motor speed is directly related to the speed of the vehicle. Motor speeds are known, those speed of the 2 robots are known to each other now. Let us say one robot's speed is S1 and for clarity let me put it here, right. So, you can see here this is robot 1's speed is S1 and robot 2's speed is S2. Now you can apply a simple logic. Is S1 greater than S2? What should you do? If S2 is greater than S1, what you should do? Both are possible. Okay. Now that you are computing, so this is very critical. Okay. So, let us look back at this code here, and this code is saying I am continuously evaluating my XYZ position relative to the other, and I am also monitoring the ultrasonic sensors. Are we coming closer to each other? That part is shown exactly here. You can see that the ultrasonic part is out there. Click on that distance, create the distance matrix of ultrasonic readings. So, that is also there, and then once they realize that let us say robot 1 is slower compared to robot 2 speed wise. So, in other words, let us say S1 this condition S2 is greater than S1, that is the speed of robot 2 is higher compared to robot 1. Then what it does is robot 1 decides to cut speed and actually come to a dead halt soon as the ultrasonic sensor says that you are in critical distance. So, the way to fuse, so it is actually a fusing method. So, what are you doing? You are fusing the data available over the communication link, with the ultrasonic sensors, and then taking an intelligent decision to halt robot 1 and let robot 2 pass, okay. And that is exactly the demo that we had seen. So, this is in brief what you should be doing, you should be coding, and all of that you can see is that logic essentially is shown here. If there is an if else condition which is essentially accomplishing that step, right. So, let us look at the transceiver script which is also pretty straightforward. This is what the transceiver does. What should it do? It should take data from the parent, pass it out on the air interface. It should obviously data is available in a particular format. So, it should pack and unpack and again pack and unpack. So, essentially marshalling and unmarshalling the data has to happen. So, it is doing exactly this. On the one side it takes it from the parent and puts it out on the air interface after suitable packing, and once it receives data from the air interface it does all the unpacking part and then gives it back to the parent, and then let the parent take a decision, right. That is all this code is actually doing. So, this piece of code, the child script and the parent script together essentially will allow you to put this demonstration in place. You can start with the basic code available on the VREP, which is nothing but the Breitenberg algorithm, for which you do not have to code anything, it will work directly, and if you have to modify it you have to do this little logic of checking the speeds and then taking a decision on which one should halt and let the other robot move forward. Thank you.